Hello, and welcome to this edition of Slice of Physics. We're now going to get into circular motion, and we're going to look at the parameters of circular motion, like period or time period and frequency. We'll also work with angles in radians and in degrees and discuss arc length. Let's discuss these concepts with the help of a couple of examples. So let's say here I have your wristwatch, and we're going to talk about the second hand going around it and making one full circle. Now the time it takes for the second hand to make one full circle is 60 seconds or 1 minute. And this letter, capital T, is the symbol for what's called period of a circular motion. So period is simply the time it takes for one full circle. The related term of frequency is simply the reciprocal of the period, so it's 1 over t always. And so for a second hand of a watch, that would be 1 over 1 minute, or I can also write that as 1 over 60 seconds. And this, when you do it in your calculator, will give you 0.0167 per second. So there's no unit in the top, and the unit is 1 over second, which can also be written as second to the power of -1. And this is given a name. The reciprocal of second is simply called hertz. So whenever you see hertz, it's just 1 over second. You also discussed frequency in terms of more familiar units of RPM and RPS. And RPM simply stands for revolutions per minute, and RPS stands for revolutions per second. That's how many times something goes around in 1 second. So since the second hand makes one full circle in 1 minute, its frequency would simply be 1 RPM. It makes one full revolution per minute of time. And if I want to convert this to revolutions per second, I can use the unit conversion techniques and set this up as revolutions per, remember per was a division, minute, and then I can convert the minute to seconds by multiplying it by 1 minute over 60 seconds. The minutes will cancel, and I will get this 0.0167 revolutions per second, and revolutions per second is the same as second to the power of -1 and hertz. So they're all different ways of calling the same thing. So just like we define period as time taken for one full revolution, frequency is denoted by lowercase letter f, and it's defined as the number of revolutions per unit of time. So let's say per second, it could be per minute, depending on what your unit is. And by the way, if I took a bigger clock, let's say a grandfather clock, its second hand also completes one full circle every 60 seconds. So its time period remains the same as your wristwatch time period, and its frequency remains the same as your wristwatch. Let's take another example. Now we'll consider the Earth. As you know, the Earth spins, and one spin of the Earth on its axis is what gives us day and night. So here's the Earth, here are some continents, and it spins on its axis with a period of 24 hours, as you know. So the time period of the Earth's circular motion as it spins on its axis is 24 hours, which is the same as 24 hours times 60 minutes over 1 hour times 60 seconds over 1 minute. The minutes cancel, the hours cancel, and you get an answer of 86,400 seconds. So that would be the time period of this circular motion. And its frequency would simply be, you can call it 1 revolution per day. We don't use RPD as a common unit, but we could call it that. There's nothing wrong with that value. But more commonly, I could say it's 1 over t. So that would be 1 over 86,400 seconds. and that gives me an answer of 1.2 times 10 to the negative 5 hertz. So you can see that the Earth takes a lot more time to spin around its axis once compared to the second hand in a watch or a clock. So the time period is a lot bigger, and because of that the frequency is a lot smaller. Frequency is an inverse relationship with time, so as your period increases your frequency decreases. So it went from 1.67 times 10 to the negative 2 hertz to 1.2 times 10 to the negative 5 hertz, 3 orders of magnitude smaller. Okay, so that was time period and frequency, and now I'm going to talk about angles and radians and arc length as we get ready for the next video to discuss things like angular velocity and linear speed in circular motion. So here are some familiar angles for you. If I ask you what this angle is, you know that it's 90 degrees. If I ask you what this angle on a straight line is, you'd say it's 180 degrees. And if I ask you what the full angle of a circle is, you know that that is 360 degrees. Now these were all in the unit called degrees. There is another unit of angle that's called radians. Some of you may be familiar with it. And the corresponding values in radians are the 90-degree angle is simply pi over 2. This pi is the same pi that you know, the irrational number that's approximately 3.14. It's the circumference of a circle divided by its diameter. And so half of that pi is 90 degrees. Pi radians is 180 degrees. 2 pi radians is 360 degrees. So if you need a conversion factor to go from radians to degrees, if I have an angle theta that, let's say, is 150 degrees and I want to go to radians, I could multiply it by a conversion factor of pi radians over 180 degrees. The degrees would cancel, and this would be 150 over 180 times pi, and I can simplify this to be 5/6 of pi. Now, when we are working with circular motion, we prefer to work with radians as opposed to degrees. So our preferred unit of measure for angles is radians. And the reason for that is because of its direct relationship to things like arc length. So let's say I have a circle here, and let's say it's got a radius of r, and I want to know what the circumference is. You know that the circumference of a circle is 2 pi r, 2 times pi times the radius. Now, if you think about the angle that that full circle has in units of radians, let's call this angle alpha. Angle alpha is 360 degrees, or it's 2 pi radians. And now you can see that the circumference of the circle was nothing but the angle that the circle included times the radius. But this equation only works when this angle is in radians, in units of radians. Now this relationship is not limited to only a full circle. So for example, if I have an arc over here that is a part of a circle and it subtends an angle of theta, as long as theta is in radians, this arc length, the length of the arc, let's call it S, arc length will be equal to the radius of the arc times the angle that it subtends. But this will only work if the angle is specified in units of radians. In this slice of physics, we got introduced to some of the parameters of circular motion, like period and frequency, and we also reviewed working with angles and radians and saw how those are related to arc lengths. Thanks, and I'll see you later.